So this is a great opportunity to be able to talk to all of you about some of the recent developments in time series, and in particular this afternoon, what I'm going to talk about is recent developments in the general area of weak instruments or weak identification. This is a topic or an area that's seen a great deal of work over the last 10 or 12 years, and a lot of new procedures have been generated, and I think a lot of new insights, empirical insights, have been gained. And so I'd like to take these 3 hours, this lecture and the next one, to go over some of those new developments, some of the motivation for it, some of the theory underlying what's going on, and then emphasize some of the tools that are available. I don't know if Mark mentioned this or not, but we were joking beforehand how this basically has the feeling of a 9-hour oral exam, where we're talking about papers that were written in the last 2 years by a large number of members of the audience, and so if you want to swap places, you're welcome to. So give us a break here in case we make a minor slip. We think we understand this material reasonably well, but I'm sure there's going to be lapses. All right, so what I'm going to talk about, this is an outline of what I'm going to talk about. I'm going to spend a little bit of time going over motivation for why we might be interested in weak instruments. I think there's a lot of topics where econometric theorists get all exercised and interested and work hard for many years, and then are ignored, and that's often the right thing to do. And in this case, it's not, because I think this has pretty important empirical characteristics or applications. I'm going to spend, actually, even though this is time series, I'm going to spend talk about time series. I'm going to actually spend about half of the time, the next 2 lectures, so all of this lecture, talking about the classical cross-section IV regression. Now, we don't actually have many of those opportunities where it's cross-section classical regression in practice, but I'm going to go over that for a couple of reasons, and one reason is that that's actually the area that we know the most about. It's the easiest model to work with, so the most progress has been made. But the second reason is that many of the lessons of the classical IV regression, cross-section regression model carry over very directly to the time series setting with modifications. Okay, then I'll talk about this in GMM, and it will all be in the context of general nonlinear GMM, although all of that will specialize to the linear case. At the end, I'm going to talk a little bit about many instruments. All of these first topics 1 through 9, so the majority of what I'll talk about, you really want to think about a case where you have a handful of instruments. Maybe a typical application might be if you were using time series data and you have a couple hundred observations, you might have instruments that would be maybe 5 or 10 or 15 or something like that, a moderate number of instruments. There are other applications where you might have many, many instruments. I'll talk about those briefly. I have some questions or skepticism about some of that. I think it's a difficult area, but so that's why I'm basically postponing that to the end. Okay, so I'd like to start with 4 examples. And the first example, the example that's got this whole literature going, was a paper by Ingress and Krueger, where they were trying to figure out what the returns to education is. And the instrument that they the regression what they wanted to regress was a regression of log earnings on years of education, and then the coefficient on years of education supposed to be the returns to education. And so there's a number of reasons why, either ability bias or measurement error or whatever, why that might not be such a great regression just by OLS. So you want to use IV methods, and their instrument was a quarter of birth. So here's the story, which is that some states allowed you to, and they used data from a long time ago, from the census. So the deal was that some states allowed you to drop out of school at a certain age. So let's say you're allowed to drop out of high school at age 16. If it's May and you turn 16, you might just hang out for another few weeks and graduate. But if you turn 16 in September, then maybe you might as well just drop out. So So that means that there might be some marginal effect, maybe a small effect, but some effect of when your birthday actually is on how many years of school you complete. Right? So that would be, and it, that would presumably be independent of measurement error or some other things like that. When you were born would be independent of measurement error and ability and so forth. That's the story. That would suggest that it would be an exogenous instrument. The thing that makes this result really interesting from an econometrics perspective is that they used 329,000 observations. So that's really great because that is as close to infinity as we're going to get in practice. So, when you see that, you think asymptotics. Okay, so that's fine. So they got a great result, which was the returns to education was 8% plus or minus 0.01. So you'd expect reasonably good precision with 329,000 observations. And then in a paper, which I understand was first presented in NBER Summer Institute, about, somebody can correct me on that one if I'm wrong, about 15 years ago or something like that. Was it a Summer Institute? Okay. John Bound and a couple of his co-authors did a simulation. And what they did is they took the actual earnings, they did a simulation, one Monte Carlo draw, and they took the actual earnings data and the actual years of education data, so this is the real data set, but then they gave people fake birthdays. Okay, fake birthdays, and then they ran IV with the fake birthdays and the real data, and they got an estimate of 0.081 with a standard error of 0.011. Okay, with 329,000 observations. Okay, so that's a wake-up call. And the problem was, and this has been studied to death because it's so interesting, is that basically the regression they ran, it wasn't just years of education, but what they actually ran was a whole bunch of interactions with the state and the year, and so they got 178 instruments. By the time you got 178 instruments, the average information per instrument was so small that despite there being 329,000 observations, essentially the instrument was very nearly uncorrelated. So if we think about instrumental variables as having two criteria, having relevance and exogeneity, let's put exogeneity aside, it wasn't particularly relevant. Another way to say it is it was weakly correlated with X. Okay, so here's a second example, a little closer to home, which is looking at regressions that are attempting to elicit the intertemporal elasticity of substitution. And so basically, if you work with the Euler equation and you linearize it, this is very standard stuff out of Campbell's 2003 Handbook of Economics and Finance. Linearized Euler equation gives you this orthogonality condition that's written down right there, and that suggests that if you have some instrument, anything that's predetermined, if this is a rational expectations orthogonality condition, then anything that's predetermined should allow you to run GMM or just straight IV. Since there's not supposed to be any serial correlation in this, right? So there's not supposed to be any serial correlation, and since there's not in practice much heteroscedasticity, this is really just an IV problem. You don't really need to worry about GMM or any of the hack or any of that stuff. Okay, so you can run this, and what Campbell reports in his handbook chapter is quite stunning results. There's really two ways you could run this. You could estimate this using a regression of consumption on the interest rate, or the asset return, or you could do it backwards, right? Because this is a first order condition, it doesn't say one of these things is supposed to be on the left-hand side and one is on the right. It's just an orthogonality condition. So it's just an equilibrium condition. So you could put it wherever you want. Either you could run it delta C on R and estimate psi, or estimate R on delta C and estimate 1 over psi. And of course, 1 over psi hat by the delta method is going to be consistent for 1 over psi, and then they're going to have variance. These things should be the same. They should be the same. You should get the same answer, and you get extremely different answers. So if you run the regression, the first regression A up there, of consumption on the interest rate, you get estimates for psi between negative 0.14 and 0.28, and the other one gives estimates of 1 over psi from negative 0.73 to 2.14. So this is completely internally inconsistent. It makes no sense. Okay? There's an easy explanation here, too. Think about this regression. You're regressing an asset return on consumption growth using an instrument. What's that instrument have to do? It has to forecast consumption growth. Okay? So you can probably forecast consumption growth, but you can't forecast it very well. Hall told us that. It's still true. Okay, so here's another one, which is the new Keynesian Phillips curve, another example. And so there's this is a big literature that we've never worked in. So I don't have any personal axe to grind here one way or the other. There's a very nice survey paper by Kleiberg and Mavridis, and that's available on their websites. So basically, there's the new Keynesian Phillips curve, and I've tacked on some sort of unobserved cost shock at the end, A to T. That doesn't need to be there. The point is that there's an orthogonality condition because of the expectations that's generated there. X is maybe an output gap, or in the way Gali-Gertler do it, it would be like a labor share, but it's some activity measure. And the point here is that the instruments then that are generated by this rational expectations orthogonality condition are going to be certainly lagged values of things that appear there, but maybe some lagged values of other stuff. And the hard part of this is, if you think about what you're doing, is these instruments have to be effective at instrumenting for pi t plus 1. All right, so what you need to do is you need to have an instrument that is going to, maybe I can just point with this instead. You need to have an instrument that is going to be exogenous. Well, that's the dating convention under rational expectations, but it also needs to be correlated with pi t plus 1 given pi t minus 1. All right, so being correlated with pi t plus 1 given pi t minus 1 is another way to say it, is that what it needs to do is it needs to be good at forecasting the change of inflation. Okay, so those of you who are in the inflation forecasting game for a living, know that forecasting the change of inflation is very, very difficult. In fact, there's this Atkinson-Ohanian paper which says that the best, at least since 1985 in the U.S., the best you could do for forecasting inflation is just model it as a 4-quarter random walk. So that's really problematic. Again, a circumstance in which you're trying to do a structural estimation, but you have an instrument that's weakly correlated with the included endogenous regressor. And the final example, which I won't go into now, but I'll give you some empirical results at the very end, is just the nonlinear version of the second example. And I'm focusing on the very simple cases. I'm not trying to. This is a model that nobody believes at this point, as far as I can tell, which is fine with me, but it's perfect. But it makes it just easy, since no one believes it. We can all agree that we'll look at it from an econometric perspective, and also it's a lot easier than the more complicated models. So I won't go through the more complicated models. All right, so this is a GMM setup. All right, but again, it's fundamentally the same problem, which is that you're going to have an orthogonality condition, and your instrument has to be correlated with consumption growth. And if I wrote down one of the more complicated models, it might be a more tractable one or pleasing one from some economic perspective, but it's going to have the same econometric problem, which is that the instruments in an orthogonality condition are going to have to be correlated with consumption growth and future asset returns. Okay. All right, so those are some motivating examples. And we'll come back and we'll look at empirical applications in all of those, except not the Ingress Krueger, because that's really not germane to this audience. Okay. So let me talk a little bit just to set the stage. So this is the back to graduate school part of everything. Go through the definitions of identification, and observational equivalence. So theta is going to be the parameter vector, capital theta is the parameter space. Two values of the parameter vector, theta 1 and theta 2, are observationally equivalent if they give the same distribution of the data. Well, that makes a lot of sense. If they give the same distribution of the data, then you're not going to be able to shift it around or distinguish between the two different points. Theta is locally identified, or that is to say, it's identified at the point theta naught. If there's no other value of theta such that they're observationally equivalent. So that just says that at least there's one value of theta naught that's okay. And theta would be then said globally identified if it's identified for all values of theta naught. Okay. In GMM, we're not actually working with likelihoods, but it's useful to think about a version of this that would be valid for some alternative objective function like a GMM or IV regression objective function. And one way we can think about that is that these objective functions would have the same value for the same values of theta 1 and theta 2, at least in expectation. And then we can go through saying it's identified at a point and globally identified in the same way. Right? So those are those are traditional or classic definitions of identification and observational equivalence. I think one of the important points here conceptually is that actually there's two points I want to make conceptually. And the first point is that is this one here, that identification doesn't necessarily imply consistency. I think we've gotten so used to thinking of identification as so you think about, say, the standard GMM definition. You go through some assumptions, and one of them is an identification assumption, and then you simply take n to infinity or t to infinity, and boom, you've got consistent estimation in an asymptotically normal estimator. So it's conventional or standard for us to think about identification as being directly associated with consistency, but that, of course, isn't true. So let me just give you this. Here's a really simple example where I'm going to give you an example where a parameter is identified, but it's not consistently estimable. And imagine you just have a process that's kind of going along for a while, and then there's a break in the mean. Well, if that break in the mean occurs after, let's say, 10 observations, and then it goes on for infinity in the new regime, I only have 10 observations at the original value. Now, that's identified. That is to say, the distribution will change as I change the value of that first period mean, but there's no way I'm going to be able to estimate it consistently, because even though my process goes on to infinity, I've only got 10 obs. All right? So identification doesn't mean consistency. The second point is that and I think it's related to that, is that we often think of identification as binary. All right, it is the way it's been defined, identification being binary or not. I mean, either it's identified or it's not. But that doesn't mean that there's this binary implication for inference. And it's useful to think about something being well identified and something being poorly identified. It's, in a very meaningful sense, sensible to say this mean in the first regime isn't very well identified because we only had 10 observations on it. If we only had 5 observations, it would be even less well identified. But if we had 50, it would be better identified. That's a sensible thing to say, and actually it's a meaningful thing to say, too, I mean, in a formal sense. Okay. So the framework in which we're going to talk about weak identification is one that has a very practical orientation, which is that I'll say that something is a parameter will be weakly identified if its distribution is an IV distribution or a GMM parameter estimated by GMM is not well. Let me start over. I will say that a parameter theta is weakly identified if its estimator or test statistics computed by GMM or IV have a distribution that is not well approximated by a normal. Right? So that is to say, we're looking at circumstances in which the usual first-order asymptotic theory doesn't really provide a good approximation to the sampling distribution. Right? I would argue, so go back to Ingress and Krueger, 329,000 observations, first-order asymptotic theory says that should be a consistent estimate. It also would have no explanation at all for why the bound, completely artificial birth dates would have produced the same point estimates and the same standard errors. All right, so we're going to focus on large sample inference. Again, that's one of the nice things about the bound application. Its sample size is large, but realistically, in what we do in macro, we have 100 or 200 or sometimes more observations. That's quite a few observations from the perspective of, say, central limit theorem, if you look at central limit theory the right way, or from consistency. So we're going to use large sample approximations, and this literature almost entirely relies on large sample approximations in one way or another. But I don't think that's a big problem. What it doesn't require is identification being strong. That is, it doesn't require identification in some sense going to infinity at the same time as the sample size. All right, and so we're going to assume instrument exogeneity throughout. That's an interesting and, of course, important question, whether something's exogenous in practice, but that simply isn't what we're talking about. It isn't what we're talking about here. Okay, so there's a couple of ways to think about weak identification. One of them, which is what I'll start out with, and that's what I'll talk about in this first lecture, is thinking about it from just a first-order condition or an estimating equation perspective. And in that, one way to think about that is, we'll see. Basically, if the z's are weakly correlated with the included endogenous regressor, then deviations of theta from its true value are not going to be something that the instrument's going to pick up at all. And because it's not going to pick it up, we're not going to be able to distinguish values of theta other than its true value from the true value. And then there's also an objective function interpretation, which I will return to when we do GMM. And finally, a couple of other preliminaries. A special case of all of this is going to be that theta is unidentified. Another special case is that some elements of theta are strongly identified and some are weakly identified. Another case is that it's partially identified. Okay, what I mean by partially identified, I mean that some elements are identified and some are unidentified. We won't come back to that again. That's just you can find all of that in the literature that I'll be citing, but it's not worth conceptually going through that. And I do want to distinguish between something that really sounds similar, but it's not at all the same, which is the notion of set identification. So set identification, which I'll be talking about set identification tomorrow in the context of SVARs. But set identification is something that's received a lot of attention in the econometrics literature, mainly in the cross-section panel literature. It's a very interesting area. That's really something quite different. What that says is that it's identified on part of the parameter space, but there's part of the parameter space in which the likelihood is flat. That is to say, there's no identification at all on another part. And then the task is to estimate the set. That's a different thing. We're not talking about estimating a confidence set. We're talking about estimating a set on which it's on which it's not identified. So we'll talk about that later. But that's not at all what we're talking about today. Okay, so I think I've said all of this stuff. Yeah, there's some literature reviews. So these are 3 literature reviews that were written at the same time that are more or less non-overlapping. So it's kind of amusing to read them. They're all out of date, but it's amusing. This is a literature review that is incredibly technical, and that's only for the strong-willed, I think. Okay. Okay, so let me get to work here. All right, so I'm going to work through this whole talk to the first bit until 3 o'clock. It's going to be entirely on the classical IV regression model. I have put subscript T's on there just because that's what I've done, but really this is all subscript I stuff, okay? I figured if I had I's and T's, we use I's to denote variable x sub it, so we're not using I's for observation, we're using T's for observation, but this is cross-sectional stuff. All right, so little y is the left-hand variable, big Y is the right-hand variable, possibly a vector, although most of what I'll talk about is just a scalar. There's a bunch of instruments, we'll call them K instrument Z. There's an additional equation, y equals pi prime z plus the error term. Let me just make a comment on this. This equation right here, in 1 second. The data are all going to be IID, so that's the cross-section assumption. So everything is IID. It's a very simple world. And for some of this, I might even want to make them normal, but I'm not going to do that for much because mainly we do asymptotics. And so then here's the equations in matrix form. So this should remind you of your undergraduate econometric class or something like that, or somewhere in an early problem set in your graduate class. And so there's the IV regression model in matrix form. Let me talk about this equation for a second. Right. So depending upon when you took your graduate econometrics, this might have been presented in some in some meaningful way as a meaningful equation. That is to say, one could ask the question whether or not this equation was misspecified. Let me suggest that that's not a valuable way to think about it. You shouldn't be thinking about the possibility that this equation could be misspecified. This equation is actually a definition of the projection of y on z. So it doesn't make sense to think about what is the remitted variable bias in pi or anything like that. That's not what pi is. Pi is just a bunch of things that are used to make the linear combination that's going to predict y. All right? So there's no room for misspecification in that equation. That's just a subsidiary equation that's sometimes useful to define v as the residual from this population projection. All right? So, so here's the two-stage least squares estimator, which in the case that we only have one instrument is just the IV estimator. And so two-stage least squares, the projection part drops out, and that's just the IV estimator. And then if I substitute in the first line y beta plus u for y, and then I simplify, I just get this final expression right here. Okay, so what I'm going to do on this one slide is going to take you through the intuition for what's going on in that bound Ingress Krueger example. And this intuition actually is the right intuition to keep throughout thinking about weak instruments. Okay? Here we go. If z is irrelevant, then that says that in this projection of y on z, in population at least, z doesn't enter. Okay? Because it's irrelevant. That's got to be true for those fake quarters of birth. In population, those fake quarters of birth get a coefficient of exactly 0. All right? Well, now I can plug this into this expression upstairs. All right? So y isn't just v in this fake quarters of birth example. Well, what's this? Z prime u is just this summation of zu, and z prime z is just this summation of zv. And now I'm going to scale it, and this is where the magic comes. I'm going to scale the denominator by 1 over the square root of t. So you've probably never seen in regression scaling the denominator by 1 over the square root of t. You always scale it by 1 over t. This guy obeys a central limit theorem. It's just zu, right? So u is just an error term, mean 0. Z is uncorrelated with a valid instrument, so z is uncorrelated with u. This obeys a central limit theorem, converges to a normal random variable. But zv also obeys a central limit theorem. Z is this random number that was generated in the computer. So the limiting distribution, the large sample distribution, when you have 329,000 observations, is that the two-stage least squares estimator subtracted from the true value is the ratio of normals. Now, if these normals were independent, that would be a Cauchy. They're not independent. But that's the distribution. So this is everything. I can have 329,000 observations and fake data, and I'm going to get a well-defined asymptotic distribution theory out, but it sure isn't what I want. Okay? Okay, now let's do a little bit more with this expression. Right, so it's the ratio of two normals that have mean 0. By the way, when you divide by a normal random variable that has mean 0, some bad things happen. Okay. All right, so this is a little bit dense, but I wanted to get it all on one slide just to show you could do it. All right? So now what we're going to do is we're actually going to show that in the bound simulation, remember how they got the same answer as two-stage least squares? We're going to show that in that simulation, actually what they're going to get is the same answer also as OLS. So that, in fact, the two-stage least squares estimator is, in the case of an irrelevant instrument, is centered around OLS. So the way I'm going to do that is I'm going to write ZU. Remember, they're jointly normal, so I can always project one of the z's onto the other one, and then I have an orthogonal error term, which is also normal. So I've just done a Cholesky factorization for all you macroeconomists. All right? So then I'm going to substitute in this Cholesky factorization, projecting the ZU on ZV into that expression for the ratios. And then I get delta plus eta over ZV. Well, now eta over ZV, remember eta by construction is a random variable that's independent of ZV. So it has mean 0, and conditional on ZV, it has this strange variance where there's actually a random variable in the denominator. It's going to be a mixture of normals, where it's an inverse chi-squared mixture of normals. But so if I think about that, so that says that this is, as I say here, it's going to be a mixture of normals, random variable, and that's in the case of this irrelevant instrument. But moreover, if I look at this expression for delta plus something that now has mean 0, well, if it has if the mean exists, it has median 0 because it's a mixture of normals around 0. If I plug that in here, and I remember, if I plug that in. Ooh, I don't know if I wrote that out. So let me just... Okay, so what's beta 2-stage least squares? Remember, beta 2-stage least squares. So beta hat 2-stage least squares now is equal to beta naught, which is this part here, plus delta plus eta over ZV. Okay? So... that eta over ZV is from this term right here, and is from that term right there. So that this thing now has median 0. It actually doesn't have any moments, but it has median 0, and that median is around beta 0 plus delta. All right, so delta just happens to be the projection in that funny definition. Well, it turns out that if you work through what OLS does, OLS has that same projection. And in fact, OLS is consistent for beta 0 plus delta. So in fact, in this circumstance, this actually is equal to the p-lim of beta hat OLS. So what's that say? It says that in irrelevant instruments, 2-stage least squares is centered around the p-lim of OLS plus something that has no moments, but median 0. So you've taken OLS and just made it much, much worse. All right. That actually makes complete sense, right? If you're doing IV with fake instruments, you can't be getting any more information than was already there in OLS, and you're making it much, much worse. Okay. And you know what's worse about it? The worst part about it is not that you're centered here, and I'm not going to go through this algebra because it's more tedious. The worst part about that bound result was not that he got the same point estimate, but he got the same standard error. That's the scary part. So it's clearly completely misleading. So if you had a standard error of infinity, that'd be okay. All right. All right, so it turns out that there's this thing called the concentration parameter, which once you start to move beyond this simple example, the example that I gave was irrelevant instruments. Irrelevant instruments is obviously an extreme case. It's useful to frame your intuition around irrelevant instruments, but it's not something we would want to develop a theory about for taking to the data. It's not like it's irrelevant or fine. There's this continuum. Okay, so that continuum is described by something called the concentration parameter. The concentration parameter is this thing mu squared. So stare at this for a little while, and this will come alive. Okay, so how will it come alive? It will. It will. Okay. One way to think about this is that this is like the explained sum of squares of the regression in the first stage regression, in the regression of cap y on z. Right? So it's like if there were a hat there, it would be exactly the explained sum of squares. So this is the explained sum of squares if you happen to know the true value of pi. Another way to think about it, and this is going to be quite important, is that if we think about the first stage regression F statistic, so that is the F statistic in which you look at whether pi hat is statistically significantly different from 0, this is close to the expected value. It turns out this is the non-centrality parameter of that F statistic. So that F statistic will be big if this is big. Right? So this is called the concentration parameter. It turns out that this is the key object in this very simple model that describes the strength of the instruments. And it does so not just in a casual way, but in a very precise mathematical way. And I put this calculation due to Rothenberg up on the slide because it's not something you would see. I mean, this is a really old handbook chapter. It's quite brilliant, but it's very old, and most people don't really read it. And I just thought I'd put this up here in case you want to work through this. The very interesting thing about this calculation is that you start here, and then you do a couple pages of algebra or something, depending on how good you are, until you get here, okay? And so from here to here is you can't see that in your head. Although you can see it's probably not unrelated, because there's things like pi prime z and stuff like that must be in here somewhere, okay? But you cleverly rearrange things because you know where you want to go. And what you get is this expression, which is very interesting. And the thing that's interesting about this expression is that every one of these random variables in this expression have a distribution that does not depend on the sample size. Okay? So there's only one way that the sample size enters through here, and the sample size enters through the concentration parameter. And if you look at this, the sample size does enter through the concentration parameter because there's this z prime z. The more observations you have, the bigger z prime z, right? So the sample size enters through the concentration parameter, but nowhere else. But what this also says is that mu, if I normalize it this way, and if mu is large, this term goes away, this term goes away, and this term goes away, and I'm left with a leading term. That leading term is actually the leading term that's left over in standard asymptotics, and it gives the normal distribution to the two-stage least squares estimator. Two-stage least squares estimators are asymptotically normal as something tends to infinity, asymptotically with respect to something, but it's not with respect to the sample size, it's with respect to the concentration parameter. The concentration parameter is the sample size. It's the effective sample size in the two-stage least squares asymptotics. If the concentration parameter is large, even if the sample size is small, it's going to have an approximately normal distribution. If the concentration parameter is small, even though the sample size is large, it will not. Okay. So I just said this. This is important. So here's a simulation from Nelson and Starts. And this is looking at the t-statistic for a variety of different values of the concentration parameter. I believe, okay, so it starts out with the dark line is irrelevant instruments. So they did another one of these Bound-Jaeger type simulations. This was in a completely different design, so it's not exactly, the distributions are different, but conceptually it's very similar. This dark line is when it's irrelevant instruments, and what happens as the concentration parameter increases is you see that this distribution of the t-statistic gets more and more peaked until then eventually it's starting to look like a normal distribution. And there really is a continuum here. This is for, these calculations were done for a single sample size, and the only thing that's changing is the concentration parameter. Okay, so let me talk a little bit about how to get a handle on this. So what's the big picture? Okay, so the big picture is we've identified what the problem is. The problem, or a potential problem, or a problem, is instruments being weak. We actually haven't come up with, at this point, any tools at all to deal with that. So what's the logical progression? The first step is coming up with some analytical framework that's going to allow us to characterize this distribution theory in a way that's more relevant than just saying asymptotic normal in the usual way. So we've got to come up with a better distribution theory. Second step is once you've done that, you can start to talk about tools, and tools that are going to work, that are going to be valid for inference when you have weak instruments. Let me say an important point about this research program and about the tools that are available. Look, the best thing of all would be to have strong instruments and not have to worry about this. Okay, so one answer, and this happens. You're in econometric seminars. I've been in econometric seminars where somebody's talking about weak instruments, and they're asked, well, what's your advice? And they say, get stronger instruments. And that's great advice for an econometric theorist to give, but sometimes it's not the most practical advice in the world. The other thing is use tools that are going to be robust, that are actually going to work if you have weak instruments. Okay, so that's actually this research program, which is coming up with tools that do the best that you possibly can in an honest way when you have weak instruments. Okay, so the first bit is what's the analytical framework. Okay, so there's 4 different things. First 3, which we're not going to use, finite sample theory. So this idea of weak instruments is really not that new. It was like Ted Anderson knew all this stuff in the 1970s, and Rothenberg knew this stuff in the 70s, and they were working on it really vigorously. But unfortunately, the tools that they were using were just tools that led to a dead end, and that's finite sample theory. And the finite sample theory just has too many things going on, and the distributions are incredibly complicated, and they're not tractable, and you can't even compute them. To give you an example, a problem that was sort of the terminal problem that they couldn't solve in that literature was what's the distribution of the two-stage least squares t statistic. Writing it out. So it just didn't work. Okay. Second idea is Edgeworth expansions. Edgeworth expansions provide approximations that are improvements upon the normal distribution. So we're trying to improve upon the normal, so let's do Edgeworth expansions. Not a bad idea. The problem, so here's the problem with Edgeworth expansions. Edgeworth expansions, I'm going to say this in a loose way. Edgeworth expansions are, you start from a normal, and then you take sort of a perturbation or an expansion around the normal. And that perturbation or expansion around the normal is an expansion that disappears as the sample size gets large, and is an approximation that's only good when the sample size is moderately large. That's all done in terms of the sample sizes, but since it's the concentration parameter that matters, in this circumstance, the Edgeworth expansion is in orders of like 1 upon the concentration parameter, and that's still not going to work when the concentration parameter is really small. All right, so that's going to be a better approximation than the asymptotic normal, the first order normal, but it's not going to explain the bound-Jaeger problem. It can never deliver that ratio of normals. The Edgeworth expansion will not be able to do that. Right, so another way to say that is that Edgeworth expansions, they were known at the time not to work, and so he's quite clear about that. But another way to say that is that they're not uniformly valid over all values of the concentration parameter. And we'd like to have inference that's uniformly valid. We'd like to be able to go from the bound example all the way to, everything's working great. Bootstrap and subsampling. I'm going to come back to this. So, a very common response, my distributions are not normal, I'm going to bootstrap. And neither of these work here. Neither of them work. All right, so we'll go over why that is. Okay. So the procedure we're going to use is something called weak instrument asymptotics, which is developed. It's not a general procedure at all. There's nothing general about it at all. It's a specific tool to solve this specific problem. To say it's not general at all, it's not out of the blue either. Essentially, this is just using a technology which is quite common in the statistics literature, which is making local approximations using something called a Pitman drift. This is something that you've seen in local to unity asymptotics, which I would imagine most of you are familiar with, although Mark and I will not be talking about these during these lectures, because they're supposed to be recent advances, and there's no recent advances in local to unity asymptotics. So what we're going to do is we're going to say that this concentration parameter is, we're going to consider asymptotics in which the sample size gets large but the concentration parameter doesn't. Well, let's go back. It's actually really obvious what you have to do. If you want the concentration parameter to be constant as the sample size gets large, well, z prime z is getting big. You're not going to change that. Those are your instruments. The only way to deal with it is if pi gets small. All right, so what's the rate at which s gets small? Well, z prime z is getting big at t, so pi better get small at square root of t. So that's it. That's all there is to it. Turns out if you plug that in, and then I won't take you through any more. All right, because so I'm supposed to, you're supposed to take people through the easy one, and then they believe you for the hard ones. All right, so here we go. So this is now going to be two-stage least squares with with irrelevant instruments. All right, so I've actually got the general two-stage least squares where we have a number of regressors. So we might have several included endogenous regressors. All right, so this is the two-stage least squares. I'm sorry, I only have one. I divided by it. So I only have one included endogenous regressor. This is the two-stage least squares estimator centered around beta 0. And so I'm just going to look at the denominator, and then I'm going to look at the numerator. So let's look at the denominator first. So the denominator, I'm going to... Okay, so the denominator, The denominator is which is y prime pzy, which is, I skipped a step. So y prime pzy is, writing that out, y prime z prime z inverse z prime y. And then if I substitute in what that cap y expression is for that, I get that first expression up there. And then I've done something again, which is going to be this little magic. I'm not going to divide by t here. I'm going to divide by square root of t. So I've got a couple of square root of t's there and a t in the covariance matrix bit. So the covariance matrix is going to be well behaved. That's just going to go to its population value. And what's interesting, okay, if I break this up, this is going to be well behaved. Z prime v is very well behaved, right? That's just this. We're in an IID setting here, so that's just something that's going to obey a central limit theorem. And then the one piece that's different is this pi times z prime z over square root of t. Well, that's set up in exactly the right way so that I can take advantage of this pi times square root of t being c. That puts another t in the denominator, and then this z prime z is going to be well behaved. So this whole thing is going to converge. It's going to converge in what? It's not going to converge in probability to anything. It's going to converge in distribution to this object here, this ratio, where now lambda has got this c prime qz. I've got a z prime z to the minus 1/2 built in here. And QZ is the covariance matrix of the Z's. And then I've got my same old ZU and ZV that we had before. All right, so it's the ZU and ZV from this irrelevant instruments problem. And so the only difference, this actually is, if you recall, the same calculation we did for irrelevant instruments. It's just that this part wasn't there. Right, so this part wasn't there, but that was that square root of t magic in the denominator, and now I've kept that square root of t magic in the denominator, but I've done so in a way that that deals with this projected part, the explained part. All right, well, I can do the same thing in the numerator, and I'm going to get a kind of similar limit. And so what I get then by putting these two together is this expression here, and this expression says that essentially the two-stage least squares estimator, subtracting out beta naught, is going to be converging not in probability, so it's not going to be consistent for anything, but it's going to be converging in distribution to this object. Okay, so let's think about the simplification that you've seen. If lambda is 0, lambda comes from this bit here. So if pi is 0, then c is 0. So for irrelevant instruments, lambda is 0. And in the case of a scalar, then these ZVs would cancel, and we're left with ZU over ZV, which is the calculation from before. Right, so all this does is it allows a non-zero, a small amount of info coming from the instruments, and then it allows for multiple instruments through that inner product. Yes?
Can you clarify how the magic here? I thought pi was set up with fixed parameters. How can you replace it with fixed parameters like square root of t?
Oh, that's a great question. I'm so glad you asked that. Well, there's the glib answer, which is I can do whatever I want. But there's the more serious answer, which is what's asymptotics for? Asymptotics is not for like proving theorems to get them published in the annals of stats or something. Asymptotics is for providing good approximations that we can use to analyze situations of empirical interest. All right, that's why you want to do asymptotics. If we could all just do finite sample, we would do it. We wouldn't have any asymptotics because we want to know the sampling distribution. Turns out finite sample is impossibly complicated, so we can't do finite sample. It's too hard. So what instead is we want to have some device, a tools that provide good approximations to sampling distributions of estimators and test statistics. In many cases, it's our textbook asymptotics. In this case, the textbook asymptotics lets us down. So we got to come up with a different tool. This is a tool. It's just a tool. Now, that said, I'm not doing this to prove a theorem. I'm doing this to provide a good approximation. If it turns out this provides a bad approximation, then we just throw it away. The reason we didn't use Edgeworth expansions provide an approximation, it turns out they don't provide a good approximation in this problem. Right? The bootstrap provides an approximation. It turns out it doesn't provide a good approximation in this problem. You can prove it doesn't. It turns out this provides a good approximation in this problem. So it's a good tool for this problem. Same thing with local to unity. I mean, if you think about the local to unity approximations, those are good approximations for that problem, and there's a lot of mileage that one can make about inference using local to unity approximations. Okay, so I've shown you sort of we've gone through the basic two-stage least squares calculation for weak instruments. I'm not going to go through any of the others. Let me just go through some of the implications here. So under this asymptotics, there are a number of implications for estimators and test statistics that we normally use in IV inference. It's important to emphasize that the reason we're using this asymptotics is because it provides a good approximation. Okay, it's not that. So these implications are implications that provide good approximations to what happens in empirical practice when you have weak instruments. Okay, so first of all, just as a technical aside, it turns out that these distributions are the same as in the exact normal model with fixed instruments but known covariance matrices, which is nice because you can draw on a rich literature. And there's a lot that can be done with that. In this context, IV estimators aren't consistent. In general, they're biased. We saw that with two-stage least squares. The two-stage least squares estimator has a mixture of normals distribution where it's not centered at the right place. The test statistics typically don't have the right distribution. So J-stats, for example, don't have the right distribution. They don't have chi-squared distributions. Confidence intervals don't have the correct coverage. We already saw that from the Bound-Jaeger thing, right? He got 0.081 plus or minus 0.011. So obviously that can't be giving the right coverage if you have irrelevant instruments. If you have irrelevant instruments, what's the only valid? Suppose now you know that those instruments are irrelevant. What's the only valid? What's a valid confidence interval if you have irrelevant instruments? So it's going to be the real line. You do a coin flip, and 95% probability you say the real line. And 5% of the time you can say whatever you want, plus or minus 0.011 or something like that. Okay, so but that's correct, because that's going to cover the true value 95% of the time, because the true value can be anything, because we don't have any information on it. It's unsettling to get confidence intervals that are the real line, but it's the right answer. Okay, there's actually a paper by Dufour and Econometrica in 1997 that makes that point. Okay. There's a problem with this distribution theory, which is that it involves mu squared. Mu squared is this concentration parameter. It's a nuisance parameter that describes the quality, the strength of the instruments. So, unfortunately, these distributions can't be used directly to obtain corrected to correct the distributions, but instead they can be used to develop theories about how to perform inference better. Okay, so what I'm going to talk about now is a little bit of detection of weak instruments, and then I'm going to talk about hypothesis tests and confidence intervals. Okay, so I'm actually doing okay. Detection of weak instruments should actually be pretty, in some sense, this is like really easy in the IV regression model. If every data set came with mu squared, so it was like at the top of the Excel spreadsheet, it had mu squared equals, then you would just know like how big mu squared is. And then it would just be a matter of doing some simulations with that value of mu squared. And then you could decide, is this instrument weak or strong? But unfortunately, the data sets don't come with mu squared written at the top. Remember, mu squared involved the true population pi. It didn't resolve the sample pi. And those aren't going to be the same thing under this nesting, or when pi is really close to 0, pi hat and pi aren't going to be the same thing in important ways. So back to Ingress and Krueger and their situation. Okay, so if we go through and we do some calculations, I can explain how this works. So basically, okay. basically here's the deal. All right, so mu squared is the non-centrality parameter of the first stage F statistic, testing the hypothesis that the coefficients pi are 0, up to a factor of k. So that says that the expected value of the first stage F statistic is equal to mu squared over k plus 1. Now, the F statistic has a distribution, so that's not like going to be the greatest way to estimate it. But basically what that says is the first stage F statistic, testing the hypothesis that pi is 0 in the first stage regression, is intimately related to the concentration parameter divided by the number of instruments, plus 1. So big values of the concentration parameter means that the first stage F statistic is going to tend to be big. Now, the F statistic is a random variable, so it's not going to be equal to this exactly, but it kind of gives you a handle on what's going on. All right, so for reasons I'll explain, concentration parameters of like 10 are pretty big. Concentration parameters of 2 are small. 30 is no problem at all in terms of the normal distribution theory. You know, you can see it all from this Rothenberg thing, right? See, look. What if I divide these things? This is just a random variable. This is like a chi-squared. And this is like a chi-squared. And this is a normal. What if I divide this by 30? And I divide this by 900. And this by 30. Well, all I'm left with is just the normal. So it's going to be normal. What if I divide it by 2? Well, I've got a normal plus a chi-squared divided by 2, and a normal, well, 2 cancels. So 1 plus a normal plus a chi-squared divided by 4. That thing's going to be really nasty. 2 is a bad number, and 30 is a good number, and 10 is like a cutoff that some people use. This all seems so easy in hindsight. Okay, so it depends on how many instruments these guys use. So when Ingress and Krueger only used 3 instruments, so they just used the quarter of birth but no interactions. Their F statistic was 30. They actually didn't like that idea. They wanted to get rid of some primary effects because they thought that, you know, maybe if you're born in January, you'd be smarter than if you're born in May or something like that. There's another reason, but whatever. Having to do with their application, they wanted to get rid of the primary effect and only have interaction effects. And so 30 was a big number, but they didn't really want to use that. So instead, they wanted to use all these interactions, getting rid of the prime effects. And in that case, the F statistic was 1.8. And so the estimate of mu squared over k is 0.8 or 0.87. And that's a very small number. Right? That's a very small number, and that's basically what the problem was. Okay. Now, there's a rule of thumb in this literature, which is to use the first stage F statistic of 10 as a cutoff. And if the first stage F statistic is bigger than 10, you can just use 2 stage G squares. And if it's less than 10, you need to worry. Let me make a comment about that. From an econometrics, so I was talking the other day to a leading researcher in this area who is in this room, and he said, I never look at the first stage F statistic in my empirical work. But he said that for the right reason. So there's a good reason and there's a bad reason to say that. And the bad reason is that you just want to ignore all of this and hope it doesn't hurt you, hope nothing, hope it goes away. Hope it goes away. And that wasn't, he actually is deeply concerned about these issues. So instead, the reason it was a good reason is he just says, I'm going to move beyond here and I'm going to use procedures for which the inference is completely robust, whether or not I have a big mu squared or not. Right? So if you are using robust procedures that work all of the time, no matter what mu is, then you actually don't need to look at the first stage F statistic and worry about it. Many people in practice do, however, like if you can run Stata and look at 2 stage G squares and then In IV Reg 2, it says first stage F statistic is a certain number, and if that number is 20, you can say, great, I don't have to do anything more. And if it's 4, then you have to start to worry. So some people like to have that cut off as a practical matter, and I can certainly see why. There's a number of ways to refine that cutoff. So that cutoff is just a rule of thumb. And so there's a whole bunch of methods that have been proposed in this area. And I think this is the most recent one, the 2005 paper is the most recent one that I'm aware of methods in this area for this sort of pretest for weak instruments. So I'll describe this method briefly because that's essentially a justification, or it turns out that yields this cutoff of 10 as a rule of thumb, and then there's reasons that you wouldn't want to use these other methods. So I'll talk about those briefly. Essentially, okay. So saying that I'm going to decide for the question now at hand is, do we have weak instruments or do we not have weak instruments? So that's a decision. You can pose that as a decision problem, and you want to have some data-based rule that is going to give you a yes/no answer to that. Comparing F to the number 10 is one way to do it. More generally, we could compare F to a critical value, some critical value, and the critical value might be 10 or it might be some other number. Let me give you one way to do this. See, here's the problem. I really don't like this slide because it involves making some approximations, and sort of, purists don't like making approximations. Here's the problem, which is, look, there's a continuum of mu squared equals 0 to mu squared equals 100, and as a practical matter, you might want to have different approaches to your data depending upon what mu squared happens to be. So you need to somehow draw the line. Any way that you draw the line is going to have an arbitrary nature to it. So here's one arbitrary way to draw the line. One arbitrary way to draw the line is I want to make sure that my value of mu squared is such that the bias of my two-stage least squares estimator relative to the bias of OLS will be no more than 10%. So I'm only 10% as bad as OLS. Okay. Turns out that's tractable. That's one thing you can say for it. So you can write down this formula here, and that's looking at the ratio of the two-stage least squares estimator or the IV estimator in a normalized to the OLS estimator. And the nice thing about that is that's a ratio of quadratic forms, and it turns out that you can solve that ratio of quadratic forms in a way that turns out to be an eigenvalue problem. And you can say what's the correlation between, what's the degree of endogeneity that's going to, in a vector sense, that's going to give me the greatest bias of two-stage least squares relative to OLS as a function of the concentration parameter. And it turns out that that's an eigenvalue problem that you can solve. And so that gives you a number. Okay, and this is the number as a function of instruments. So K2 is the number of instruments. And if you have a small number of instruments for bias is equal to 10, the cutoff number is maybe 4 or 5 or 6 or 7 or 8. And then it sort of, bias of 10%, then it sort of asymptotes out here to 10. You can actually prove that this asymptotes to about 10. Okay, so then you can say, okay, so this is the concentration parameter that I'd like to have. And now remember, the F statistic is related to the concentration parameter because it's the non-centrality parameter of the F statistic. So you can then say, I want to have a test based on the F statistic related to a critical value. Well, that critical value now is going to have to be based on the non-central F distribution with this concentration parameter. So that's the procedure, and so that's what the test is. And so the general version of this is something called the Craig-Donald statistic, and so you compute the minimum eigenvalue of essentially a matrix F statistic. So it's a matrix version of the first stage F. If you have multiple included endogenous regressors, then your first stage regression is multiple regressions, right? And so then there's going to be a matrix F statistic, and then the minimum eigenvalue of that is something called the Craig-Donald statistic. And we want to test. Craig-Donald introduced this to test for non-identification. We are totally uninterested, by the way, in non-identification. Right? I don't care if it's unidentified. That's not interesting. We're not. It's so. A senior colleague of mine many years ago, when I was first thinking about this, said, well, this is really not an issue because all you have to do is just test whether that pi is 0 or not. But you see, the whole point is that that's not good enough because pi can be small. You're not interested in rejecting whether it's 0 or not. You're interested in it being big enough, in mu squared being big enough that the distributions are well approximating a normal. And having it reject 0 isn't going to ensure that those ultimate distributions are going to be good approximations to normals. Okay, so you need it to be bigger than that. And so we're not going to be testing the null of non-identification. We're going to be testing the null that this minimum eigenvalue of that ratio up here is at least a certain value. All right. So anyway, this is all implemented in software, and then there's some critical values. And you know what? These critical values, if you want to have this 10% ratio, these critical values are like 10. Well, they're 11 or 10. So here's these critical values, but they're like 10. So I say just use 10. Although people do use these critical values. Okay, so there's other tests to use. There's other tests that are available. We propose some other ones that are not as desirable for a variety of reasons. I think one important reason is that what we're really interested in is we're interested ultimately in having as much inference as possible to be fully robust to this concentration parameter. That is, to work uniformly in mu squared as long as the sample size is large. And pretesting doesn't really fit into that framework very well. It certainly doesn't fit into that framework in terms of tests because we actually have hypothesis tests and confidence intervals. We, meaning the literature, has hypothesis tests and confidence intervals that are in fact uniformly valid. And so thinking about this as a testing problem is not, I think, very helpful. Thinking about an estimation problem, estimation is much harder, as I'll come back to later. So there is some validity to it in an estimation sense, I guess. There's a couple of other procedures. Hahn and Hausman have a test in econometrica, and the intuition of their test is pretty cool. Remember that intertemporal elasticity of substitution example in Campbell's handbook chapter, where you estimate it one way and you got one number, and you estimate it backwards and you get another number, and those numbers are supposed to be the inverse of each other, but they weren't at all. So that suggests intuitively that what you could do is you could take those two and then you could do some sort of delta method type calculation. You could see whether one is different than another in a statistically significant sense. And that's what Hahn and Hausman do. So it's a nice idea. So that's actually now going to be, since if you think about the asymptotics, they're supposed to be close to each other. So you're testing the null that they're close against the alternative that they're not, which means you're testing the null of strong identification against the alternative of weak identification, which is the opposite of that F statistic rule. The F statistic rule was testing the null of weak identification against strong identification. Unfortunately, this test actually has no power to speak of. So it actually doesn't reject against the null of non-identification. You could put in non-identified data, and the trouble is the numerators will be really different, but the denominator will be really huge. So it turns out that this test statistic doesn't actually provide any power. So it turns out, and Hausman's a co-author on this paper. So it turns out that this is not a great idea. Okay. there's actually a whole bunch of, in Stata, as far as I can tell, at least as far as I can tell, the way Stata is programmed is that every time there's a new test proposed, they just add one on, but nothing's ever deleted. So it seems as though there's like 27 test statistics or something for weak identification in Stata. Most of them are not, in fact, any good. Okay, hypothesis tests and confidence intervals. All right, so as I mentioned before, it's useful to make a distinction between fully robust methods and partially robust methods. A fully robust method is one that, at least when the sample size is large, is going to work well uniformly in mu squared. Mu squared could be 0 or 2 or 10 or 500, and it's going to work equally well. The coverage is going to be good for a confidence set. The rejection rates under the null are going to be 5% for a test. And so that's, in some sense, what you'd like to do, is you'd like to have a fully robust method. And then if you can't do that, you could have partially robust methods. And those would be methods that are going to be less sensitive to weak instruments than two-stage least squares. Well, it turns out that for tests, it turns out that that these procedures are really well developed, and there are quite a few procedures now, at least in the IV regression case, for fully robust inference. And I'm going to go through some of those. So this literature is in a state of evolution. It's not a finished product. And the researchers have done very sensible things, which is they started at the easiest, and they're working their way towards the hardest. And the easiest thing of all is IV regression with one included endogenous regressor. And the testing problem in that is, I think, solved in terms of first-order asymptotic theory. So that's really great. But then the next step is two regressors, and it's not solved. There's some ideas floating around, and I'll talk about them. And then another problem that's much harder is estimation, and there's not. I'll give you some thoughts on that, but there's not a lot of good ideas. You know, this is part of our bad habits in teaching graduate students econometrics. You know, out of green, it's just like, you know, root t beta hat minus beta goes to normal 0 sigma squared, and so then you go beta hat plus or minus 1.96 standard errors, and you think about those as being the same thing, and they're not the same thing at all. Okay, so testing and hypothesis testing on the one hand and estimation on the other are just completely different objects. And it turns out that in the case, there actually exists, in effect, a uniformly most powerful procedure, uniformly in mu squared, for hypothesis tests in the single included endogenous regressor problem, and no one has a clue about estimation. That's a little bit strong, but it's approximately true. Okay. All right, so let's just think about two-stage least squares and fully robust testing. So the two-stage least squares t statistic, remember I showed you those plots, those simulations by Nelson and Starts back in 1990. That has a really nasty distribution that we might be able to even see it here. Okay, so one approach is you could take a distribution like this, and then you could look over all possible. You say, I don't know mu squared. I don't know mu squared, but I could look over a range or some large range of mu squared, and I could take a worst case critical value here and a worst case critical value here, and then I could use that for my inference. But as you can see from the two-stage least squares t statistic, that's going to give you really idiotic critical values. You'll reject for minus 1.96 or something, but the other one up here is going to be, plus 10 or something like that. So that would be one approach you could use for testing, but it's a bad idea. So using adjusted critical values based on distributions that are highly sensitive to instrument strength is not going to be a promising approach. So there are other approaches that are more promising. One of them is to use a distribution, this approach number 2, to use a test statistic whose distribution doesn't depend on mu squared. And you might say, well, gosh, why have we been spending all of this time worrying about worrying about all of these perverse problems when there's distributions, statistics that don't depend on mu squared, and in some sense that's a great question. So we could just do that. And then there's a third approach. These are good, but it turns out they're not ideal. And then there's a third approach, which really was pioneered by Marcelo Moreira, which is using statistics whose distribution depend on mu squared, but then evaluate those statistics conditional on a sufficient statistic for mu squared, so that you can get rid of the dependence on mu squared and you can do conditional inference. So I'll talk about approaches 2 and 3. Approach 1, some of the very first papers in this literature tried approach 1, and then you do some simulations and calculations, and it turns out it's a bad idea. So I'm not going to pursue it. Approach number 2. So this is in the nothing's new under the sun category, which is that there is a statistic which dates back now 60 years. You know, it's amazing. I was at a conference, I guess 2 years ago, and I was just giving some talk, and I was looking around the audience, and there was Ted Anderson in the audience. And so Ted Anderson is this guy who, in 1949, with Rubin, figured out this test statistic, and he's still an active econometrician. It is a very it's a thing to think about, actually. It's very impressive. Anyway, what the Anderson-Rubin statistic does is it's incredibly clever and simple idea, which is it says the following thing. I know how to test the hypothesis beta equals beta naught in a way that doesn't depend on the strength of the instruments, and here's how I'm going to do it. I'm going to hypothesize my value. Well, since it's hypothesized, I can compute y minus y beta naught. I can just compute the residual under my hypothesized value. If that hypothesized value is the truth, under the hypothesis that it's correct, then that says that the error term is supposed to be uncorrelated with z. Right? So the residual here, under the hypothesis, is just u, which is uncorrelated with z because z is exogenous. So I can regress this on z and check whether z has a non-zero coefficient. So I can compute the f statistic in the regression of y minus y beta naught on z, and that's what it is. And in the case that you have normal errors and exogenous x's, this has an exact f distribution. All right? So that's the Anderson-Rubin statistic. So this is really clever. So you didn't need the strength of the instruments, and the reason you didn't need anything about the strength of the instruments is there's no first stage regression. Right. So you're hypothesizing this, and then you just project it on z. Under the null, this thing has an f statistic. Now, under the alternative, if you get it wrong, if your value of beta naught is not the right number, if it turns out you're wrong, then that says that you've got some of the cap y in here. So you're going to reject, but it actually depends on the strength of the instrument. So if the instruments are strong, strongly correlated with cap y, if you're off by a little bit, it's going to pick that up. On the other hand, if the instruments are weakly correlated with cap y, then you could probably be off by quite a bit and it's not going to pick that up. So the power of this statistic against an alternative is going to depend upon the strength of the instruments and the concentration parameter, but the validity under the null does not. All right, so that's method number 1. That's Anderson-Rubin statistic. Okay, so I just said all this. You don't need normality, so I said exact f, but of course it's just asymptotically chi squared k over k under usual central limit theorem assumptions. And this is uniformly valid in the strength of the instrument. So that's procedure number 1 that works all the time. Okay. Okay. So here's some advantages and disadvantages. It's easy to use. I think that it's important to think about this for 1 second. There's something very bizarre about the Anderson-Rubin statistic in practice. So let's just look at this for a second. Suppose, where's my, okay. So here we are in our regression of y minus y beta naught on z. Suppose that beta is at the true value. So you're right. You know beta naught but the instruments are not exogenous. Okay? Then this is going to reject. So there's a very difficult aspect of interpretation of the Anderson-Rubin statistic, which is that under the null of exogenous instruments, under the joint null of exogenous instruments in beta equals beta naught, it has an asymptotic chi-squared k over k distribution. But it can reject for two reasons. It can reject for non-exogenous instruments, and it can reject because beta is not equal to beta naught. Now, the way that Anderson-Rubin statistics are used in practice, and I'll go through this, is by inverting the Anderson-Rubin statistic to construct a confidence interval. So you find the set of values of beta naught that are not rejected by the Anderson-Rubin statistic. You can have a very small confidence set for two reasons. A reason that you like, because you have strong instruments and good inference, or a reason you don't like, which is that your instruments are kind of not exogenous. So you can get a lot of precision falsely because of non-exogenous instruments. It requires a fair amount of, this is a subtle thing to interpret. I mean, you just have to understand, this is just what it is. Okay, there's another test, Kleibergen's LM test. This is the other statistic I'm aware of that doesn't depend on mu squared. It has advantages and disadvantages. Its advantage is that it's pretty easy to implement and it's available on some software. Disadvantage is that it has some very strange power properties. So I personally don't recommend this. There's another test that dominates both of these called the conditional likelihood ratio test. Okay, so let's go back to your first course in statistics in graduate school, and I'm sure you will all remember the definition of sufficiency. That if you have a statistic S with a distribution that depends on theta, and T is a sufficient statistic for theta, then the distribution of S given T doesn't depend on theta. And so what that says in our problem at hand is that we can think of S as being a test statistic that's testing beta equals beta naught, and then T is some statistic that's sufficient for, well, what's theta? Theta in our case is mu squared. So that these test statistics, every statistic we've looked at except for just these two LM and AR depend on mu squared in their distributions. But if we can have some statistic that's sufficient for mu squared, at least under the null hypothesis, then that suggests that we will, in fact, be able to compute we'll be able to look at the statistic of S, but then conditional on T, it doesn't depend on theta. What does that mean? What that means is operationally, what you would do is you compute two statistics. You compute S and T, and then to reject S, you have to look at a table of critical values. That table of critical values has one row of it is the value of T. So you look down that row for the value of T, you look down that row for the value of T, and then you read over to the percentile. So that's the sense in which you'd be doing conditional inference. You're choosing your critical value based on the value of this other test statistic, or the other statistic T. All right, so that's actually what Morera pursued in his thesis and in a couple of papers. And there's this 2003 Econometrica paper where he proposes a particular approach, which is using a likelihood ratio statistic. And so S in that case is going to be a likelihood ratio statistic, and then there's some other object. And I think I have a slide giving it for completeness, but it's some nasty-looking creature that is the sufficient statistic. So the sufficient statistic is this object right here, QT, which is this element in this thing. Everything here is internally defined, so you could actually compute everything based on everything here. I checked that. That doesn't mean you have any idea what's going on. Okay? And then but basically he's got a statistic that's sufficient for mu squared. It turns out, when I first saw Morera's paper, the first question I had is, why you aren't just conditioning on the F statistic? And it turns out that's not the right statistic to be sufficient for mu squared under the null hypothesis. So that's actually sort of a deep contribution of his paper, is figuring out what the right conditioning statistic is. You can condition on the F statistic, but it actually isn't going to deliver inference as powerful as this. Okay, so that's a nice paper. Okay, so anyway, that's so how do you implement it? The tedious way to implement this is you could have a big table, you compute the likelihood ratio statistic, you compute QT, you look it up in a table. It turns out that this has all been programmed up, and thanks to Anna Makusheva, you just type something in Stata, and it all works really well. Okay. So it turns out that this is, so why is this? This is actually, I think, the recommended procedure. So when I said I think the problem has been essentially solved in the case where there's a single included endogenous regressor, what I mean to say precisely is that the problem of hypothesis testing of beta equals beta naught and the problem of construction of confidence intervals has been essentially solved to first order asymptotics, at least, in the problem of a single included endogenous regressor, and the solution to that is actually using the conditional likelihood ratio statistic, which is this Morera statistic. The only downside is it's kind of complicated, but that's just the way it is. There's software that does it. Now, I hope this. Let's see if this. All right. So. If I have this going, let me see if I have this going. I want to show you some power curves. All right, so what we're looking at here is the quality of the graphics is not so terrific. So what we're looking at here is power curves, and this is from a paper in Econometrica with Morera and myself and Don Andrews. And so what this does is it evaluates what's called a power envelope, which is the envelope of most powerful tests that you could have. And so that power envelope of most powerful tests, there's this mu squared problem, and then there's the alternative that you're testing against. And so in principle, you have a very rich family of optimal tests that's now got parameterized in 2 dimensions, mu squared and the alternative. You can derive optimal tests in these circumstances, and what we're looking at here is cycling through a variety of values of parameters. And the best line here, the farthest up line, is actually theoretically the best that you can possibly do with normal errors. In the usual t-statistic problem, that when we go plus or minus 1.96 standard errors, we do that so routinely that we don't really think about it. It's quite remarkable. That statistic is in the classical setting uniformly most powerful for testing beta equals beta naught, or at least asymptotically has that interpretation. That doesn't happen very often in the rest of statistics. That's a very special problem. It's an important problem, but a special one. So instead, there's usually a family of best tests, and Mark touched upon this in the problem for break testing, and this is just like the problem for break testing, something where there's a family of most powerful tests. And in general, no one dominates the other. The remarkable thing about this series of plots is that if you look at this heavy dash line, which is called CLR, this heavy, not this one down here, this heavy dash line is essentially always on the power envelope. And you almost can't even see it because it's so much on this one here that's not moving is the Anderson-Rubin statistic. So as the number of instruments increases and as the correlation increases, the Anderson-Rubin statistic can have pretty weak power. This one here is this Kleiberg and LM statistic. So the Kleiberg and LM statistic has really strange power properties in the sense that you can be more likely to reject a close value than a distant value. There's this non-monotonicity in the power function for the LM statistic. When you invert it, that results in confidence intervals that will that have strange. The Kleiberg and LM statistic, when you invert it for a confidence interval, if I remember this correctly, it contains the limited information maximum likelihood estimator, but it also contains something you could define to be the limited information minimum likelihood estimator, which is the wrong eigenvalue of the liminal problem, and that corresponds to these points over here. So anyway, what this is all supposed to do is impress upon you the idea that this conditional likelihood ratio statistic of Morera is on the power envelope essentially all of the time. That is to say, it's effectively uniformly most powerful of all of this family of valid tests. So it turns out this uniformly most powerful result is something that holds. This uniformly most powerful result is something that holds among all tests, both conditional and not conditional, for beta equals beta naught in this problem of a single included endogenous regressor. So basically, a fair amount of computer power and hard work has gone into this, but it seems as though the conditional likelihood ratio statistic is really the by far clearly the best test to use. So let me just talk very briefly before we break about confidence intervals. Testing and confidence intervals are the same problem. Estimation and confidence intervals are not the same problem. Standard errors are not involved with this. All right, so go back to hypothesis testing basics, and hypothesis testing basics and confidence interval basics. So a 95% confidence interval is a set valued function of the data that contains the true value in 95% of all samples. Equivalently, or alternatively as a construction method, you can think about constructing a confidence set as the set of values that cannot be rejected as true by a test with a 5% significant level. So those are just those are equivalent statements. So confidence sets come from inversion of test statistics. And normally we think about this as being beta hat minus beta naught over a standard error plus or minus 1.96. Okay, so if this is the hypothesis test, so right now I've set this up in a hypothesis testing framework. This is the t statistic testing the hypothesis with beta hat equals beta naught, and I will reject if it's less than 1.96 or greater than 1.96. But in flipping this around, pulling standard errors over to the other side, I get the usual algebra that delivers a plus or minus 1.96 standard error confidence set. But that's very special to the fact that inversion of the t statistic literally entails no more than just multiplying both sides by the standard error. When it's a more complicated function of the data, you can't do something as simple as that, but you can nevertheless find the set of values that are not rejected when taken one at a time as the null hypothesis, and that constructs a 95% confidence set. As I mentioned this Dufour paper, which says that these confidence sets, if the situation is unidentified, in the case that's truly unidentified, if 100 John Bounds walked into the room with their fake data, if their procedures were correctly working, 95 of them should have had the real line as their confidence interval. And that's what this Dufour paper says. So the Anderson-Rubin statistic has that property, and the CLR has the property. And so in terms of construction of them, it's actually rather straightforward. Just for the Anderson-Rubin, you just fiddle around with the quadratics. When you have more than one, you can do it. Here's some references when you have more than one. I won't go through that. And then there's some other papers that are working on the case of more than one coefficient. Okay. There's a variety of possibilities that can arise when you have an Anderson-Rubin confidence interval. It can be disjoint. It can be unbounded. It can be empty. And so I think the same thing is true for the CLR statistic. The CLR statistic, thanks to Anna Makusheva's paper and Brian Poy's software. This is all something that can be implemented. The Anderson-Rubin statistic, the CLR statistic will always contain the liminal point estimator, which is one nice feature of it. Okay, what I'm going to do is we're going to break now, and I will come back looking at an example of these hypothesis tests. Which is by going through an empirical example, which is a paper by Motoyogo in Restat a few years ago, where he looks at this linearized consumption CAP-M, trying to estimate the this intertemporal elasticity of substitution psi, and I'm not going to really focus on the results as much as just on the methods that he uses and sort of typical things that he finds. So I don't know if this is going to. I hope this is visible on your printout. These on the handout, the slides. But this is a table of some first-stage F statistics that he found in this data. And remember, the puzzle was that you could run basically two-stage least squares either direction, and you got answers that just were not internally consistent. And what he finds, just for starters, here is for the two-stage least squares, just for the instruments that happen to be used in this example, which I'm not even going to go into because I don't really care about the example particularly. It's just an illustration. The instruments that he used really did a fairly mediocre job of predicting consumption growth, which is no surprise. Consumption growth is really tough to predict. And then this is, I think this is return on equities, and not surprisingly, he had a tough time predicting the stock market too. So the first stage F statistic is quite low, and that's and that was actually true for other countries as well. You really couldn't predict consumption growth in the stock market in many of these countries. Let me digress just for 1 second. Something that came up at the break, somebody asked me a question about first stage F versus the R squared from that regression. Sometimes people look at the R squared from the first stage regression. Let me give you 2 reasons why that's not the statistic to look at. Reason number 1 is that, and the most important reason, is that you can have an R squared of, say, 15%, and an R squared of 15% with 20 observations indicates not a lot of movement in the data that's going to be useful for identification, but an R squared of 15% with 2,000 observations is a lot of movement that's useful for identification. So the non-centrality parameter for an R squared of 15% with 2,000 observations is going to be quite large. The non-centrality parameter for an R squared of 15% with 20 observations is going to be quite small. It's the non-centrality parameter that matters, not the R squared. And the second reason is that another problem with the R squared, and you see this is really irritating. Sometimes people report R squared for first stage regressions, but that includes not just the instruments, but it includes the other included exogenous regressors as well. And that has no relevance at all. What matters is the marginal predictive content of the instruments above and beyond the included exogenous regressors. So reporting the R squared for the whole kit and caboodle is a completely meaningless statistic. It's the F statistic testing the hypothesis that the coefficients are 0 on the instruments. So if you have additional exogenous regressors in there, it's only the instruments. Okay. Then he just finds that there's some. This is just this table of results where you get mutually inconsistent values in 2 psi g squares for psi and 1 over psi. Let me point out just one thing. He produces a couple of other estimates, something called Fuller K, which I'll talk about very briefly, and Limmel, limited information maximum likelihood. Let me point out something about Limmel, which is it appears as though 34 is the inverse of 0.3, and in fact it is the inverse of 0.3. So Limmel is the one estimator here that actually is normalization invariant. That's the way it works. So the Limmel estimator does not, by construction, have this inverse problem. That doesn't mean it has a normal distribution. It just happens to be the case that it doesn't have this inverse problem. All right. So here's some confidence intervals, and so what he finds. So this is really hard. Okay. So these are weird confidence intervals. These are confidence intervals for psi constructed in 3 different ways. So he finds for the US, the Anderson-Rubin confidence interval is empty. Now that doesn't mean that you have a precise estimate. What that means that there's no value of beta naught, of the intertemporal elasticity of psi. There's no value of psi that is consistent with the orthogonality conditions. This is based on using the 2 equations, both the stock market and the bond return. So there's an equity premium thing. So that's what's going on, okay? So that actually makes sense. There's no value of psi that is consistent with both the equity and bond returns not violating the orthogonality restrictions. So that's okay. This null confidence interval is okay. Now, so he finds one that's okay. The LM, we're not going to look at because I don't like the LM statistic because of its quirky properties. The conditional likelihood ratio statistic, it actually looks like it gives you, well, it's centered around 0, which is a little bit odd, but it looks like it gives you reasonably precise inference. Taking these two together would say that your exogeneity, your rational expectations conditions, your predictability conditions are being rejected, so it doesn't make a lot of sense to use this as a confidence interval. Right? It's not as though you would say, I've answered the question, the intertemporal elasticity substitution lies in this range, and ignore the fact that that's inconsistent with your orthogonality. Instead, the model is rejected. Right? So that's how I would read this line. Now, there's also intervals that give the real line. That's okay. If there's weak instruments, that's not necessarily a bad thing. All right, so here's some other ones that give the real line. All right, so that's just an example of the sorts of things that you can get. But getting the real line is actually, in some circumstances, the right answer. When you have very little information, you want a procedure that tells you that. It's not the most thrilling thing if you're trying to publish a paper, but it's correct. All right. All right. So extensions to more than one include an endogenous regressor. There's work by Kleibergen, a 2005 paper that's not listed here, 2007 paper, and there's other work that I'll talk about later. Okay.